Now the next part of Chapter 13 is dealing with sections 7 and 8. This is going to be fairly short and quick, but we want to talk about solution dilution and solution stoichiometry. Short number of slides, but hugely important in terms of implications for calculations. So now that we've looked at molarity, very often what's going to happen in a laboratory setting is that you are going to find that your solutions or compounds come in a concentrated form called a stock solution. And this makes perfect sense because why should you pay for water, which if you're talking aqueous solutions, you're paying for water if you buy dilute solutions, and you're paying to have water shipped. And water is very heavy and costs a lot to have shipped. So what a lot of companies will do is order a concentrated solution and then use that and dilute it down to make the concentration that they need of a less concentrated amount. So you buy a stock solution and then you have to figure out how to dilute it. So we're familiar with the idea of dilution. Dilution is simply adding solvent, in most cases water, to your stock solution. But how do we determine how much of the stock solution to use? Well, what we're going to do is use this relationship right here. M1V1 equals M2V2, which is another one of these equations that if you're ever going to get that totally nerdy chemistry tattoo, that's one you can have tattooed. That's one you need to just inscribe on your brain. M1 and V1 stand for molarity and volume of your initial concentrated solution, your stock solution. Okay, so that's referring to stock. Okay, there we go. Stock. I got a little too far off the edge there, sorry about that. M2 and V2 are the molarity and volume of the diluted solution that you want to make. That's what you want to end up with. The reason this equation works is because the molarity multiplied by the volume gives the number of moles of solute. Okay, so moles of solute before. If all I do is add water, the number of moles of solute does not change. Only the amount of water, the amount of solution changes, but the moles of solute are not changing. It's the same in both solutions. What you have to keep in mind, this equation applies only to dilution when I am adding water to make a diluted solution. It does not apply to what we'll be talking about in a minute, which is stoichiometry. So if you are looking at two different chemical compounds, you cannot use this formula. Only if you are dealing with one compound and you're simply adding more solvent to dilute it. That's the only time you can use this. Now, there are times in stoichiometry you may, if you've had a chemistry class before, seen this done. It works only if the compounds are in a 1-to-1 ratio. You'll get the same number, so it looks like it works, but the reasoning, the concept behind it is completely wrong, and you will eventually get tripped up on that when you don't have a 1-to-1 ratio. So keep in mind you need to be able to distinguish dilution from stoichiometry, where you're trying to compare two different chemical compounds. And another little safety note we're going to throw in here, just a bonus, it's not in your book, but when you're working in the lab and you're carrying out a dilution with concentrated acid, there's a rule of thumb that says when you're diluting an acid, always add acid. So it's AAA. Always add acid to water. Never add water to a concentrated acid solution. Now, you don't always have a problem with it, but what can happen is that when you mix water with concentrated acid, it's a very exothermic reaction. It's going to get hot, and when you're adding the water to the acid, what may happen is that the water is not mixing in. It creates a localized pocket. It can get hot enough to create a little bubble of steam, and it will cause concentrated acid to spatter out. It will start to bubble or splash. It'll splash back on you. It'll spit up into your face. Or the other thing is, you can see here, you get a lot of degassing, and that gas is usually hydrogen gas, which is very irritating, and you don't want to breathe that in. So you always want to pour some water in a container and then add the concentrated acid to the water. It will still get hot, but water has an enormous heat capacity, so the heat generated can very quickly spread through the water. And the other thing is, if you do get a little pocket of something, as it tends to bubble up, what it's going to bubble and spit back at you is water, not concentrated acid. All right, so let's look at an example of dilution. Now, there's a figure in your book that shows the physical dilution of this. If you want to look, figure 13.8 on page 463. It's an image like the one we showed earlier of making the 1 molar sodium chloride solution. But you have a 12 molar stock solution of potassium chloride. Okay, so that is molarity 1, stock solution. And you want to use that to make 5 liters of 1.5 molar potassium chloride. Okay, that is what I want to end with. That's my dilute solution. It gave me the volume and the molarity of my end solution. So that's M2 and V2. I have M1. So what I'm looking for is what volume of that stock solution do I need in order to prepare 5 liters of 1.5 molar potassium chloride. If I start with my initial formula, M1V1 equals M2V2, what I can do is solve for V1, what I'm looking for. So divide both sides by M1, M2V2 divided by M1 will give me what I'm looking for. And then I just plug in the numbers. 1.5 molar or moles per liter of the dilute solution times the 5 liters that I want divided by 12 molar. Now notice here they broke molarity up into its mole per liter and then canceled it out. It's perfectly fine to leave it just as molar because the molarity will cancel out as well. And then that tells me the volume in liters. Okay, so I need 0.625 liters or 62.5 milliliters of stock solution to make 5 liters of what I'm looking for. So how would I make that? I'd measure out 62.5 milliliters of my stock solution. I would pour it into my volumetric flask that's 5 liters, and then I would add water and mix thoroughly. That would give me the solution that I'm looking for. All right, so we're not going to spend a lot of time on dilution, but be aware that's a very important skill to have. You'll be using that in lab starting this week and then continuously for other labs from here on out. All right, now solution stoichiometry. This is different from dilution. So if I have a reaction which involves reactants and products that are in aqueous solution, often it's convenient to specify the amounts of reactants or products in terms of volume and concentration rather than in terms of mass. So you've been doing stoichiometry with mass up to this point, but if we want to look at aqueous solutions, it's easier to talk about the concentration of the solution. So if we have a concentration and a volume, that's the same as the number of moles we'd get from a mass and a molar mass. So we calculate number of moles of reactants or products, and then we just continue on with stoichiometry just like we've been doing. All right, so this should look fairly familiar on the solution map. So volume of A, we find moles of A, we go from moles of A to moles of B based on stoichiometry. Okay, that goes in right here. Stoichiometry is here. This is concentration that we're going to use, and now we can use concentration again to get from moles to volume. Okay. This is exactly the same as what we've been doing with other stoichiometry, only instead of grams and molar mass, we're using volume and molarity. Okay, the mole to mole, exactly the same. So looking at an example of this, now here's my equation, my balanced equation. H2SO4 in aqueous solution, so sulfuric acid in aqueous solution, plus 2 moles of sodium hydroxide in aqueous solution yields 1 mole of sodium sulfate and 2 moles of water. Now, as soon as I see that I have a balanced equation, it is immediately telling me this is not a dilution because I have more than one chemical component that I'm trying to relate. I'm trying to relate, if I read, 0.125 moles of sodium hydroxide solution. How much of that do I need to neutralize 0.225 liters of 0.175 moles of sulfuric acid? Okay, so I'm relating sodium hydroxide to sulfuric acid. I cannot do it as a dilution. Does not work. I have to use stoichiometry in this case. So what I'm going to do is start with what I know about the sulfuric acid, because I have two pieces of the puzzle there. Okay, so what I'm trying to figure is how much of that 0.125 molar sodium hydroxide solution I have. So since that's what I'm looking for, let's start at the other end with what I know. I know that I have 0.225 liters sulfuric acid, and it's 0.175 molar. If I have a volume and a molarity, that is going to tell me the number of moles. So volume times molarity, if I use this value right here, that's going to give me number of moles of sulfuric acid. Okay. Now, if I want to compare moles of sulfuric acid to moles of sodium hydroxide, I have to go back to my balanced equation. I have to use my stoichiometry. So when I look, there are 2 moles of sodium hydroxide for every 1 mole of sulfuric acid. That step right there is why using dilution won't work, because it is not 1-to-1. It's 2-to-1, and I have to put that relationship in. Once I have the number of moles of sodium hydroxide, now I can use that other bit of information they gave me, the molarity of the sodium hydroxide, which is the moles per liter, to get from moles to the volume that I need. Okay, so when it says how much sodium hydroxide solution, it wants to know in liters. So when I plug everything in, here's the volume of the sulfuric acid, the number of moles per liter, so that's molarity right here. Okay, here's my stoichiometry right here. Okay, and another molarity right here, and that leads me down to the volume that I need, 0.630 liters of sodium hydroxide solution. So as I said, pretty quick, but those are very, very important concepts to understand. They are very mathematical, so the best way to learn those is just to practice those. So grab those homework problems out of the back of the book, go to Mastering, work on those problems. Be sure you understand the difference between dilution and stoichiometry for solutions. In the last part of Chapter 13, we're going to look at some of the properties of solutions, such as freezing point depression and boiling point elevation, and then the idea of osmosis. These are known as colligative properties. So we're going to look at colligative properties of solutions.